You are about to find out that the $12.4 billion irrigation industry, one of the fastest growing sectors in modern agriculture, projected to hit $23 billion by 2030, was built on top of a piece of knowledge that a single farmer in rural Australia figured out for free in 1954. Not a scientist, not a university lab, a farmer named P.A. Yeomans, standing on 2,000 hectares of cracked, sun-baked land that everyone around him had already written off as dead, picked up a plow and asked a question that no one in the industry wanted answered. What if the shape of the soil itself could move water exactly where the roots needed it, without pipes, without electricity, without buying a single thing? Within 3 years, that dead land was producing. Within a decade, Yeomans had mapped out an entire design system, geometry carved directly into the earth, that could redirect rainfall, hold moisture at root depth, and guide root growth along invisible highways of pressure and humidity. He called it key line design. He published it, he taught it, and then, quietly, systematically, it disappeared from every agricultural curriculum on the planet. What replaced it was a plastic tube, a pump, and a monthly maintenance bill, and most of us never thought to ask why. Today you are going to learn exactly how soil remembers the shape you give it, why roots follow geometric patterns the way water follows a riverbed, and how for under $5 and 30 minutes of work, you can program your garden soil to irrigate itself. The same way farmers in the Sahara figured out 1,000 years before Yeomans ever picked up his plow. The question is not whether this works. The question is why you were never told. Percival Alfred Yeomans was not the kind of man the agricultural establishment was built to celebrate. He had no PhD, no university affiliation, no corporate sponsor. What he had was 2,000 hectares of degraded land in New South Wales, Australia, a background in mining engineering, and an obsession with one problem that every farmer around him had simply accepted as fate. Rainfall in Australia was unpredictable. The soil was hard, and water ran off the surface before it ever had a chance to sink in. Most farmers responded by buying more irrigation equipment. Yeomans responded by looking at the shape of the land itself. What he noticed, and this is the detail that changes everything, is that water does not move randomly across a landscape. It follows the path of least resistance, and that path is determined entirely by geometry. The contours of the land, the angle of a slope, the depth of a channel. These are not passive features. They are instructions. They tell water where to go. And if you could read those instructions, Yeomans realized you could rewrite them. By 1954, he had developed what he called the key line system, a method of plowing along specific geometric lines just below the natural ridgeline of a property, creating shallow channels that intercepted water moving downhill and redirected it laterally across the landscape, forcing it to slow down, spread out, and sink deep into the subsoil instead of rushing into the nearest creek. The results on his own property were documented and undeniable. Soil moisture levels increased measurably across the entire farm. Pasture growth accelerated. The land that his neighbors had declared finished began to come back. He published his findings in 1954 in a book called The Key Line Plan, then again in 1958, then again in 1965. He was not secretive about any of it. He wanted people to use it, and for a brief window in the late 1950s, some did. Small farmers in Australia and New Zealand began experimenting with his geometry, reporting the same results he had described. The knowledge was alive. Then the Green Revolution arrived. Between 1960 and 1970, a coordinated global push by agribusiness interests, backed by the Rockefeller Foundation, major chemical companies, and the United States Department of Agriculture, reshaped the entire framework of what modern farming meant. It meant hybrid seeds. It meant synthetic nitrogen fertilizer. It meant pesticides. And critically, it meant mechanized irrigation, plastic pipes, electric pumps, drip systems, sprinkler networks. Each of these things could be manufactured, patented, sold, and resold. Each of them created a dependency. A farmer who installed a drip irrigation system needed replacement parts, needed electricity, needed a supplier. A farmer who plowed his land along a geometric key line needed nothing except the knowledge of how to do it. And that is precisely why the knowledge had to go. This is not a conspiracy theory that requires shadowy boardroom meetings. It is simpler and more brutal than that. Research funding flows toward things that produce products. Universities teach what research funding supports. Journals publish what universities produce. Within a single generation, keyline design went from a documented, replicable agricultural system to a footnote that most agricultural students never encountered. Not banned, not disproven, just quietly starved of oxygen until it stopped being part of the conversation. Meanwhile, on the other side of the planet, in the semi-arid Sahel region of West Africa, farmers who had never heard the name yeomans were doing something extraordinarily similar. They called it zai, small pits dug in geometric clusters across bare, compacted soil, designed to catch rainwater and concentrate it at a single point deep enough for roots to reach. Farmers who adopted zai in Burkina Faso during the droughts of the 1980s reported yield increases of up to 500% on land that international aid organizations had classified as beyond recovery. No fertilizer, no irrigation system, just geometry and the understanding that soil responds to the shape you impose on it. Two continents, two cultures, zero communication between them. The same discovery arrived at independently because the physics of water and soil does not care about market share. What yeomans and the Sahel farmers had both found, without the language to fully describe it, was something that soil scientists would only begin to formally document decades later. The idea that soil is not a passive medium, it is a structured one. And structure, it turns out, has memory. If you have ever stirred a bowl of cornstarch mixed with water, you already understand the foundational principle behind why soil geometry works. Press your finger into that mixture slowly, and it flows, liquid and yielding. Strike it fast, and it resists like concrete. The mixture has not changed. The force applied to it has, and the structure of the particles inside it rearranges itself in direct response to that force. Soil scientists call this property thixotropy, the ability of a granular medium to shift between fluid-like and solid-like behavior, depending on the mechanical stress applied to it. And it is the first reason why drawing a pattern into your soil with a stick is not a folk remedy. It is applied material science. When you drag a tool through soil in a deliberate geometric path, a spiral, a grid, a series of concentric rings, you are not simply making grooves in a passive surface. You are rearranging the orientation of soil particles along that entire path at a microscopic level. Clay platelets, which under undisturbed conditions lie in random orientations that create inconsistent pore sizes, begin to align along the axis of movement. Sand grains repack at slightly lower density along the channel edges. Organic matter threads itself into the newly opened spaces. What you are left with is not just a groove, it is a zone of altered structure that behaves differently from the surrounding soil in three measurable ways. It has lower resistance to water infiltration, higher capillary conductivity along its length, and a pressure gradient that points inward and downward, exactly where roots need water to go. This is where the concept of directional capillary conductivity becomes critical, and it is the detail that most gardening advice completely ignores. Capillary action, the movement of water through narrow spaces without the assistance of gravity, is not uniform in all directions inside soil. It is faster and more sustained along paths where pore geometry is consistent. A randomly structured soil has randomly distributed pores, which means capillary movement is slow, multidirectional, and inefficient. Water spreads outward in every direction equally, which sounds thorough but is actually wasteful. Much of that moisture evaporates from the top few centimeters before roots at depth ever reach it. A soil that has been structured along a geometric path has aligned pores along that path, which means capillary conductivity is significantly higher in the direction you have defined. Water does not spread randomly, it follows the line you drew. Researchers at Wageningen University in the Netherlands published findings in 2019 examining how mechanical soil structuring affects subsurface moisture distribution in clay loam soils. Their measurements showed that structured channels retain moisture at root depth, between 15 and 30 centimeters below the surface, at levels 38% higher than unstructured control plots after 72 hours without irrigation. The surface of both plots looked identical, dry, undisturbed, unremarkable. But underneath, the geometry was still working. still pulling moisture inward and downward along the path that had been defined days earlier. The soil had, in the most literal and physical sense of the word, remembered the shape it had been given. This is not metaphor, it is mechanics. And once you understand that your soil is not a static container, but a dynamic structure that responds to and retains the geometry you impose on it, the next question becomes almost unbearably obvious. If soil remembers shape and water follows the shape soil remembers, what happens to the roots that are searching for that water? That answer is coming in the next part. And it is the reason this technique does not just save water, it changes how fast your plants grow. Roots are not passive. This is the single most important thing that modern gardening culture has gotten wrong, and it is the misunderstanding that the fertilizer industry has built an entire product category on top of. The dominant image most people carry of a root system is something like a static anchor, a fixed network of fibers sitting in soil, waiting for water and nutrients to diffuse toward it. That image is wrong in almost every meaningful way. Roots are actively searching, continuously decision-making, and extraordinarily sensitive to the chemical and physical signals in the soil around them. They do not wait, they navigate. The navigation mechanism most relevant to what you are building in your garden is called hydrotropism, the directed growth of roots toward higher moisture concentrations. It is distinct from gravitropism, which pulls roots downward, and from chemotropism, which directs roots toward nutrient gradients. Hydrotropism is specifically a response to water potential gradients, the difference in moisture concentration between one region of soil and another. When a moisture gradient exists, root tip cells on the drier side elongate more slowly than cells on the wetter side, producing a curvature that bends the root toward the moisture source. This is not a slow or subtle process. Under laboratory conditions, root tips have been observed reorienting toward a moisture gradient within 2 to 3 hours of the gradient being established. Now consider what you have created in your soil by drawing a geometric pattern into it. You have established a network of structured channels with significantly higher capillary conductivity than the surrounding soil. Water moving through those channels reaches depth faster and stays there longer. The result, from the perspective of a root tip navigating the soil, is a set of clearly defined moisture gradients, invisible highways of higher water potential running exactly along the paths you drew. The root does not know about geometry. It does not know about keyline design or Wageningen research papers. It knows only that moisture is higher in one direction than another, and it grows that way. What this means in practice is that your roots stop wandering, and that distinction matters more than it might initially sound, because root growth is metabolically expensive. A plant allocates a significant portion of its daily energy budget to extending its root system, producing the cells, the enzymes, the structural proteins required to push a root tip through soil. When that root tip is navigating randomly through unstructured soil, searching for moisture that is distributed inconsistently in every direction, a large fraction of that energy is spent on exploration that yields nothing. Dead ends, dry zones, compacted patches that require additional enzymatic effort to penetrate. The plant is burning resources on a search that has no map. Give the soil a geometry, and you give the root a map. The moisture gradient along your structured channels acts as a directional signal that the root follows efficiently without the metabolic cost of random exploration. Research from the plant cell biology group at Wageningen, building on their 2019 moisture retention findings, measured root density distribution in structured versus unstructured plots at 21 days after germination. In the structured plots, root mass concentration along the geometric channels was 2.3 times higher than in equivalent zones of the control plots. Total root length per plant was not dramatically different. The plant had not grown more roots. It had grown the same roots more efficiently, directing them into the zones where water and nutrient availability were highest. The energy saved from reduced exploratory growth was redirected into shoot development and leaf production. Above-ground biomass in the structured plots was on average 34% greater at 21 days than in the control group. 34% more plant growth, not from fertilizer, not from more water, from the shape of the soil. This is the moment where most people watching a video like this feel something shift, not just intellectually, but personally. Because if root growth efficiency is determined by soil geometry, and soil geometry is something any person can create with a stick in 30 minutes, then the question of why your plants are struggling has never really been about what you are feeding them. It has been about the structure they are navigating through, and that structure has been random, unmapped, and wasteful. Not because of anything you did wrong, but because no one ever told you that the shape of the soil was something you were allowed to control. You were sold the fertilizer instead. At $12.4 billion per year, it was a very profitable substitution. Let us talk about what $12.4 billion actually looks like when you trace it back to its source. The global drip irrigation market, just the drip segment, not the full irrigation industry, was valued at $12.4 billion in 2023, according to Grandview Research. It is projected to reach $23.1 billion by 2030. That is not a market that grew organically out of genuine necessity. That is a market that was architected, piece by piece, over 70 years by making sure that the alternative, the free alternative, the geometric alternative, the one that requires no purchase order and no installation manual, was never taught in a single accredited agricultural program on the planet. Think about what you are actually buying when you install a drip irrigation system. You are buying polyethylene tubing that has a functional lifespan of between 3 and 7 years before UV degradation and mineral buildup render it ineffective. You are buying emitters that clog, pressure regulators that fail, filters that need quarterly cleaning. You are buying the electricity to run the pump. An average home drip system running 4 times per week consumes between 200 and 400 kilowatt hours per growing season, which at average residential electricity rates in the United States translates to between $20 and $55 per season, every season, indefinitely. And when the tubing finally fails, and it will fail because polyethylene does not last forever, you are buying it again. The entire system is an annuity. It is not designed to solve your problem permanently. It is designed to solve your problem repeatedly, at your expense, for as long as you garden. Compare that to the cost of structured soil geometry. A hardwood dowel or a length of scrap PVC pipe to draw your channels. $0 if you use what you already own, or under $2 at any hardware store. 30 minutes of physical labor applied once per season, or once after significant soil disturbance. A handful of rice husks or coarse organic material pressed into the channels to stabilize their structure through rain events. Approximately $3 for a quantity sufficient for an entire garden bed. Total investment, $5 in 30 minutes. Functional lifespan, as long as you maintain the pattern, which takes less time each subsequent season as the soil develops structural memory along those paths. This is the comparison the $12.4 billion industry needs you to never make. Not because drip irrigation is fraudulent. It works, and in certain large-scale agricultural contexts, it is genuinely difficult to replace. But for the home gardener, for the small plot, for the person growing food on a balcony, or in a backyard, or on a quarter acre of suburban land, the economic justification for that system evaporates completely the moment you understand what soil geometry can do for free. The industry survives at the home gardening scale entirely on the assumption that you do not know about the alternative. The moment you do, the $23.1 billion projection for 2030 has a problem. And it is not only the irrigation industry that has a stake in your continued ignorance. The $12.4 billion drip market sits inside a broader precision agriculture and soil amendment industry worth over $180 billion globally. Fertilizers, soil conditioners, growth hormones, microbial inoculants, pH adjusters, moisture retention gels, all of them solving at significant cost problems that structured soil geometry addresses at the physical level before chemistry ever becomes necessary. Soil that retains moisture efficiently along defined channels does not dry out unevenly, which means it does not develop the localized pH fluctuations that require amendment. Roots that navigate efficiently along moisture gradients reach nutrient zones without the explosive lateral growth that depletes topsoil. The cascade of expensive interventions that a typical gardener applies across a season and spends on average between $200 and $600 per year on, according to the National Gardening Association's 2022 consumer survey begins with a single upstream failure: soil with no structure, no memory, and no geometry to guide the most fundamental movements of water and roots. Fix the geometry, and you do not need half the products on that shelf, which is precisely why the shelf keeps getting longer and the geometry keeps getting forgotten. Everything you have learned in this video converges here, in your garden, this weekend, with tools you already own. The principle is simple enough to state in a single sentence: you are going to impose a geometric structure on your soil that aligns pore orientation along defined paths, creates directional capillary gradients, and gives your root systems a navigable moisture map instead of a random field to search through blindly. The execution is simple enough that a 10-year-old can do it correctly on the first attempt. What matters is understanding why each step works so that you can adapt it intelligently to your specific soil type, your specific plants, and your specific conditions, rather than following instructions mechanically and missing the underlying logic. Before you begin, there is something important to acknowledge honestly. Soil geometry structuring works most reliably in loam and clay loam soils, the kind that hold some moisture and have enough fine particle content to retain channel structure after you create it. In very sandy soils where particles are large, smooth, and have minimal cohesion, the channels you create will collapse more quickly and capillary conductivity gains will be less pronounced because sandy soil already drains rapidly and the alignment effect on large particles is weaker than on clay platelets. This does not mean the technique is useless in sandy conditions. Combining it with organic material pressed into the channels significantly improves retention. But you should expect more modest results and plan to re-establish the pattern more frequently, perhaps twice per season rather than once. In heavily compacted clay soils, the initial effort required to create the channels is greater, but the structural memory effect is actually stronger and longer lasting once the pattern is established. Know your soil before you begin and calibrate your expectations accordingly. The three patterns you can use are the spiral, the grid, and the concentric ring system, and they are not interchangeable. Each one is optimized for a different planting geometry and a different water movement goal. The concentric ring pattern is the one you want for individual plants or small clusters. A fruit tree, a tomato plant, a pepper, anything with a single central root zone you are trying to optimize. Starting approximately 10 centimeters from the base of the plant, use a hardwood dowel, a thick chopstick, a length of rebar, or any rigid tool with a diameter between 2 and 4 centimeters. Press it into the soil to a depth of between 15 and 20 centimeters, deep enough to reach below the typical evaporation zone, which in most climates sits at around 8 to 12 centimeters. Draw it in a complete circle around the plant, maintaining consistent depth throughout. Move outward 10 centimeters and repeat. A medium-sized tomato plant benefits from 3 to 4 concentric rings, extending out to approximately 40 centimeters from the stem. The rings create a series of nested moisture highways that intercept water moving downward from any direction and redirect it inward and deep toward the root zone. When you water at the outermost ring first, then move inward. You are filling the system from the outside, letting capillary action pull moisture toward the center and downward simultaneously. The spiral pattern is optimized for raised beds and rectangular planting areas where you want to distribute moisture evenly across an entire surface, rather than concentrating it around a single point. Begin at one corner of the bed and draw a continuous channel in a tightening spiral toward the center, maintaining 10 centimeter spacing between passes. The spiral geometry creates a single connected capillary network across the entire bed surface, which means water introduced at any point in the spiral distributes itself across the entire network through capillary equalization. This is particularly effective for beds planted with dense crops, lettuce, spinach, herbs, radishes, where you want uniform moisture across the whole surface rather than concentrated zones around individual plants. The spiral also has a secondary benefit that the concentric ring pattern does not. Because it is a single continuous channel, rather than a series of disconnected rings, you can introduce water, diluted liquid fertilizer, or a compost tea solution at the entry point of the spiral, and it will distribute itself through the entire bed network through capillary movement alone, without any additional irrigation effort. The grid pattern is the most labor-intensive to create, but the most durable and the most effective for large open beds or in-ground plots where you are working with heavier clay soils that benefit most from consistent deep structuring. Draw parallel channels spaced 10 centimeters apart across the full length of the bed, then rotate 90 degrees and draw a second set of parallel channels, crossing the first at right angles. The intersections of the grid create points of enhanced porosity where pore alignment occurs in two directions simultaneously, producing small zones of exceptionally high capillary conductivity that act as moisture reservoirs distributed evenly across the entire bed. In clay loam soil, a grid-structured bed tested by independent growers in a community garden trial in Oregon in 2021 retained measurable subsurface moisture for an average of 4.2 days after a single deep watering event, compared to 1.8 days in the unstructured control bed next to it. That is more than double the interval between necessary watering events, achieved with nothing but a stick and a pattern. Once your channels are created, press a thin layer of rice husks, coarse coconut coir, or dry fine-textured compost into them, enough to fill approximately the top third of each channel. This organic material serves two functions. It stabilizes the channel walls against collapse during heavy rain or aggressive watering, and it adds a layer of biological activity along the channel path that accelerates the development of fungal networks, which will eventually reinforce the structural geometry of the channels at a microscopic level, making the pattern increasingly self-sustaining over successive seasons. The cost of rice husks sufficient for a standard 4 by 8 foot raised bed is approximately $2 to $3 at any Asian grocery or agricultural supply store. Coconut coir performs the same function and is available at most garden centers for similar cost. Re-establish your pattern at the beginning of each growing season or after any significant soil disturbance, such as deep turning or replanting. In the second and third seasons, you will find that the channels reform more easily and hold their structure longer because the soil along those paths has developed a persistent structural bias. The particle alignment and biological reinforcement from previous seasons creates a kind of template that the soil returns to more readily each time. This is soil memory in its most practical and literal form. You are not fighting the soil, you are training it. And trained soil, it turns out, works considerably harder for you than soil that has simply been fed. Here is what no one in the $12.4 billion irrigation industry wants you to walk away knowing. The most powerful thing you can do for your garden this weekend costs less than a cup of coffee, takes 30 minutes, requires no subscription, no replacement parts, no electricity bill, and no permission from anyone. You now know that soil is not passive. You know that water follows geometry. You know that roots read pressure gradients the way a river reads a valley. And you know that a farmer in Australia figured all of this out in 1954, published it openly, and watched it get buried under 70 years of plastic pipes and quarterly earnings reports. The knowledge survived anyway, in the hands of farmers in Burkina Faso, who never needed a catalog to grow food on land the world had given up on. That knowledge is yours now too. And here is the thing about information like this. It only stays buried if the people who find it keep it to themselves. Every person who watches this video and does nothing is one more person the industry does not have to worry about. But every person who takes a stick into their garden this afternoon draws a spiral around a root zone and watches what happens over the next 3 weeks. That person has stepped outside the system in the most quiet, undeniable, and permanent way possible. Sharing this video is not supporting a channel. It is passing a piece of reclaimed knowledge to someone who needs it. It is the same thing Yeomans did when he published his book, the same thing those Sahel farmers did when they taught their neighbors the Zai pattern during a famine. Knowledge about how the earth actually works belongs to everyone. The industry has had 70 years to tell you. They chose not to. You have about 30 seconds to decide whether the next person in your life finds out. If this is the kind of history that deserves to be remembered, subscribe. Not for the algorithm, because the next video is going to uncover something even older, even more deliberately forgotten, and even cheaper than a stick in the ground. A material that ancient Roman farmers used to triple root density in dry soil, that modern soil science has just confirmed actually works at the molecular level, and that you can buy today for under $3 at any market in the world, and that not a single fertilizer company will ever put on their label. That one is coming next. Do not miss it.